Hey everyone, can you hear me?
Yeah, we can.
Okay. I'll just wait for like 5 minutes more and then I'll start. How are you guys doing? Everything fine with you? Alvin and Moaz, how are you guys doing? Okay, anyways, I'll just start because I'm not expecting many people. Um, like people who have already come, that's fine. And then I'll go on and explain. Like we'll go through the session, and then you guys can feel free. You guys can stop me at any time and ask questions. It's a very one-on-one session sort of because there are not a lot of people. So just feel free to stop me anywhere and ask anything in my slides. So I'll just start. So I'll just share my screen. Okay, can you guys see my screen?
Yeah.
Okay. All right. So I will. Today's topic is DDPG and policy gradient. Um, and paper that it is based on is this one by Lily Crabb and others from 2016. Let me just open the paper. Yeah. So this is the paper. So in general, what the paper is doing is it's talking about a new algorithm called deep deterministic policy gradient. So it's called DDPG because the formula form is deep, which DDPG, which is deep deterministic policy gradient, and it's an addition or a combination of two popular algorithms, DQN and DPG. Um, so so I'll just go skim to the paper, and then I'll go through the slides. And just feel free to stop me if at any point in time. If we'll start, like we'll just start skimming through the thing. But if you don't understand certain part of the paper, or you want to know more about one part of the paper that I didn't properly say or didn't properly explain, then you can just stop me and say, "Oh, what is this part doing, and what is this paper about? Like in this section, what is the section about, and so on." Okay, so here they're talking about how DQN is like been one of the cornerstones of AI development, of reinforcement learning. And here they're talking about uh, how DQN is good, but it doesn't work with high dimensional um, action spaces, high dimensional observation spaces, and discrete and low dimensional. Uh, how DQN only solves high dimensional observation spaces, but can only handle discrete and low dimensional action spaces. So let's say if you have a continuous action space, which is if your actions are, let's say, between -1 and 1, then you have to do some kind of a discretization to make sure that your actions are um, they're discrete and not continuous. Because if they are continuous, we can't use TQN to learn from it, and it is very apparent if you see how we learn from DQN. In DQN, whereas there's one network called the Q network, which takes in an input the state and produces values Q of SA1, SA2, SA3, and so on until SAN. And then because these are like countable finite number of elements that it outputs, therefore if you have a continuous domain, you have to think of a different strategy, because the output here is discrete, and what you want is an output which can work with non-discrete cases, like continuous cases. So for that, the motivation is that we can use DDPG. Okay, here they are saying that we combine DQN with actor critic method. For using the actor critic method uses DPG. So I'll explain what actor critic is and what DPG is and how DPG works as well. Um, then they discuss the background for reinforcement learning, like what is a Q function, what is the Bellman update, what is the loss function for learning doing Q learning, and what are the targets for Q learning. So all of this has been discussed before, but if you have a question, you can stop me here and ask something if you want to. Any question in the notation here? What does this mean? Like this is just saying that it's the reward that you get throughout the episode when you start from SI, ST, and AT. This is just discounted reward starting from ST and AT. This is a Bellman equation, but it's not the exact Bellman equation. It's not a Bellman equation um, for uh, for the optimal policy. It's a Bellman equation for normal policy. So it's a recursion on the normal policy. You can use this as an update if you want to. This will correspond to the source update actually. Okay. Um, and then we go to the algorithm. So in the algorithm, they discuss what is happening, like what is their algorithm. So they discuss that there is something called as DPG, in which you can take the gradient, like we can compute the gradient of an actor function. So what is an actor and what is a critic? We'll go through that in the slides, but the the main takeaway from this equation is that it can be used to compute an update to the actor, and the critic we can always update using the Bellman equation. So that's our actor critic method in a nutshell. And then they're discussing in their algorithm what else are they doing which is different. So they're using a replay buffer for sure, just like in DQN, and they're updating the weight slowly so that the method is stable in learning. And then they also suggest using batch normalization if you want to if you want this approach to scale up. So um, finally, they discuss the importance of exploration noise. So basically, whatever their network outputs, like whatever action it outputs, it's not enough to explore the entire world. So they add another noise term, which they compute at every time step. And using that, making the output of the actor noisy, they are able to move around and check for, like, they're able to figure out, do exploration, and um, yeah, they're able to do a better exploration than without the noise. In particular, they use the Ornstein-Uhlenbeck process. If you want, like, Ornstein-Uhlenbeck process is a simple um, noise. The stochastic process, basically they use it as a noise generating mechanism. So it is actually moving from a place to another place, and you can set its parameters, and then it will give you some noise values. Okay. So that's pretty much it in the algorithm section here. And then we have the result section in this paper. Um, so I'll go through this algorithm once more in the slides. But in terms of the paper, we have they do experiments in continuous control task. Um, and they also do experiments on Torx, which is a racing simulator. So it looks like this, and the Mijoko simulator looks like this, um, and the Torx one looks like this. And there's some videos. We will go and look at those videos. There's some graphs. We also look at those graphs, and then they discuss other related work, which is not in our scope right now. But um, it is. It's worth reading, like what are the other methods that were also going on around this time. This is a paper from 2016. So what are the other papers that were working, that people are working on around this time? It's TIPO, PILCO, and then there is GPS algorithms and other sides of algorithms, like not important for our discussion today, but it's always worth a read to know what are the methods were there. And in conclusion, they are just talking about the fact that stable learning is possible using their method, and how their method doesn't require as much steps as you would think, but only requires about like 22.5 million steps of experience, which is very low compared to Atari, which was like 20 million or 100 million steps of experience. So they also discuss, like, finally they discuss the limitation, um, that there are lots of episodes are needed to find solutions, which I feel like is not a major issue, because, like, I think they just put this paragraph in here to say that they have limitations, but uh, it's not really a limitation in my view, because uh, like a lot of algorithms require a large number of training episodes to find solutions, and if you want to be sample efficient, you have to go and use some kind of model based technique or something. So that's the paper in here. Any questions about the paper? If there is no question, I will go to the slides. Any question about this paper, any part of this paper? If you want, you can open this link by just, if you want to see it on your own computer, you can just go to google.com and then search for DDPG paper. And then you'll see that the first paper, continuous control, is the paper, and you can open the PDF here. So if anybody has a question, they can ask me now in this paper. I'll wait for 2-3 minutes and then I'll proceed to the presentation. Okay, I don't think anybody has a question, so I'll just move to the next topic. Basically the same topic. I'm just going to move the slides. Um, so the discussion today is about policy gradient and DDPG. What is a policy gradient and what is DDPG, right? So in general, this is what we'll go through today. The most important part is this part where I discuss different um, parts of policy gradient. So it's not necessary to know policy gradient, but I think like there's no other like in this reading group we have never discussed it, and it seems like an important part to be discussed. So that's why I'm discussing it along with DDPG today. And in general, like what I'll do is I'll recap reinforcement learning, Q values, and Q learning. Then I'll go through the challenges of Q learning and then policy gradient, variants of it, uh, active critic stuff, active grading methods, and then deterministic policy gradient and deep deterministic policy gradient. And then we'll discuss the results and conclusions from the paper. As always, just feel free to stop me at any moment and ask questions if you want to. Okay, so what is happening in reinforcement learning? There's an agent which interacts with the environment E over a number of discrete time steps. So time step 1, time step 2, time step 3, and so on. At each time step, the agent receives a state ST. It performs an action AT according to the policy pi. And in return, the state transitions from ST to ST plus 1 and a reward RT is received. And the process continues until the terminal state is reached. So after it reaches the terminal state, it just doesn't do anything more. The episode is finished. And graphically, we can represent it this way: like you choose an action, you have a state. Both of these determine what R1 will be, and then they also determine what the next state will be. And then next state and A2 determine what R2 will be, and they also determine what S3 will be. So you can see the transition function in the MDP is like ST plus 1 depends on ST and AT, and RT depends on ST and AT. So that's basically roughly that graphical model that people use for the Markov decision process. It's a graphical model is basically showing dependencies between different random variables that we're using to be more technical. Okay. So in reinforcement learning, the goal is to maximize an expected long-term discounted reward. So by that, what I mean is that usually there is some reward, like you can if you can sample trajectories. What you want is that this notion of reward plus the next reward plus the next reward and so on until the infinity, or until a fixed horizon. You can sum that up and you want to maximize that rather than maximizing the immediate reward. And then you can add gamma to the reward if you want to have a fixed horizon. Like adding a gamma will basically zero the r k at some k, and it will lead to fixing the frame that we are considering. So if the gamma is, let's say, 0.99, then maybe let's say it just this gamma to the power say 15 is maybe too small. So let's say gamma to the power 15 is 0.01. If you have 0.99, then it will only look at 15 steps. And what we want is that out of many trajectories um, that we can sample, uh, we want to maximize the expected long term the expectation of the long term discounted reward. So this is the long term reward, and the discount is the gamma that we're adding to it. Any questions here? Okay. Yeah, if you have any question, just let me know. Like if you even have lingering questions about a concept that I talked before, uh, then just ask me. I'll go back as well. Okay. All right. So Q values. Let's recap a little bit of Q values. Q value is the expected return for selecting action A in state S and following a policy pi. So it just is the same as the long-term discounted reward. But the reason I'm mentioning it here is because we're using DQN as well. So uh, the main idea is that, yeah, the q value will denote like what happens if if you're in the state S initially. You take an action A. What is the maximum? What is the reward you will get over a long-term discount, over a long period of time? So you will get the reward Ri at immediate step, like Ri, where Si and Ai is S and A. So you get Ri initially, then you get Ri plus one, then you get Ri plus two, but you discount the future rewards. And similarly, there is something called as an optimal action value function, where the Q star, which is like it is the same thing as Q pi, but the difference is that while Q pi is for pi, this is for an optimal policy of pi star. So, what is an optimal policy? An optimal policy is a policy which will select the best action at any time step, and it is going to lead to it will basically maximize this objective. And how do we know that this is equal to this? Because we can see the recursion here, right? So Q of SA is the reward that you get initially, and then plus gamma times this part is a recursion part. So you can say that this part is actually Q pi of SA, which is Q star. In this case, it is Q star of SI plus 1, AI plus 1. But because this is an optimal policy, we know that out of all possible AI plus 1, we want the best AI plus 1. Therefore, this is gamma max AS Q star AI plus 1, SI plus 1, and AI plus 1. Okay. This is all stuff from previous reading groups, and I'm just mentioning it here because we are going to discuss because there's a part of this equation where we have DQN. Okay. Then we can discuss like we had this recursive equation can be used to learn q learning can be used to do q learning. And how we do it is that we take the value and then we add a change that like this will slowly move it towards the correct value of QSA. And what is this value? This value is basically the target value. This is the target value, and this is the output value, or this is the actual value at that time. And the target value is like this because we know that from Bellman equation, the reward plus gamma max of next action of Q star S I plus 1 AI plus 1 is what we are looking for. And therefore, this is the part which we have copied from here. So if we want to do Q learning, what we will do is create targets of this form, and then make sure that our Q values move towards that target. Okay. All right. Next, let's discuss what are the challenges of Q learning. So while it is okay to use Q learning for a very high dimensional observation space, because that is feasible, because initially we are going to apply some kind of convolutional layer to reduce the size of the state. We can't do it for the action because the actions are not input directly, but the deep Q network has outputs corresponding to each action. So the issue is, let's say there's an action which is in a continuous range -1 to 1. So should we make 10 intervals? Should we make 100 intervals? And each interval, like the more you make the intervals, the more you want to be precise about which action you should take. The more this output will be, and the bigger this number of output nodes are, the harder it becomes to train this algorithm with DQN. And also, like if you have more intervals or big action space, then it's hard for an agent to explore efficiently. Okay. So that's the reason that we can't just normally use DQN here, because in DQN there's an inherent assumption that there's like a finite number of actions which are discrete and low dimensional. Okay, let's see, like we'll see how to overcome that basically we will have another network, and that is going to output a certain value, and because of that value we'll be able to solve this dilemma or this problem of blowing up the output space. Okay, so just like Bellman equation allows us to learn optimal policy gradient technique can also allow us to learn optimal policies. In general, what policy gradient method does is that it gives you a way to update your policies. So what do you mean by policy? How can you update a policy is the question, right? So uh, we assume, like in actor critic methods or policy gradient methods, we assume there is a parameterized policy. So that means that there is a policy which takes in a state, produces an action, and it has some neural network parameters theta. Uh, in that case, we want to optimize and make sure that the theta, pi of theta, is able to produce, um, like it becomes the optimal pi of after some updates. So to know how to change this, we need to have a notion of what it means to what it means for a policy to be doing good, and how good is a policy is the question. This question can be answered as follows: a good policy is something which leads to a good long-term episodic reward, and a long-term episodic reward is this r tau, which is a if you sample a trajectory, if you move according to the actions proposed by this pi, then the reward of this trajectory, the expectation of this reward is the expected long-term reward, and it is the same objective which we had in the Q learning as well. Okay, so this is the same objective, but let's see how we can use this to compute and update to the policy. So we want to learn the best theta so that j theta is maximized. So theta star is actually argmax of j theta, and this is the equation that we just saw. This to know the best maximum value of this, we have to maximize over this part, and we can do that by using gradient descent, because we are maximizing. If we were minimizing, it would be gradient descent, but here we are maximizing, so we can do it using gradient descent. What we will do is basically we'll have start with some theta 0, and we'll move towards theta 1, theta 2, theta 3. We'll do a number of iterations, and at each iteration what will happen is that we'll add a term which is the gradient of the score that we just proposed. The score is this value j, which tells you how good your parameters are, and using this equation we can always move towards the maxima of this curve. So the maxima of this curve is where we maximize j theta, and where we maximize j theta we get the best theta, which is the best good policy. So any question in this part? What are we doing in gradient descent, and what is this policy objective? Okay, so let's see again. What, like, this is a very minor derivation, or it's not a very big derivation, but what is the gradient g nabla theta j theta? The policy gradient can be computed as well, you have nabla theta j theta, which is equal to the nabla theta, and then this is the gradient with this of this thing, and you can open this expectation, and when you open the expectation we'll have a probability of the trajectory tau, the reward tau, and d theta, and we're going to take the gradient of this whole thing with respect to theta. So we can move the gradient inside the expectation, and when you do so, only this part depends on theta and this part doesn't, because this part is the sum of rewards output by the environment. So only this part depends on theta, and therefore the nabla only applies to this part. The gradient only applies to this part of the equation. And since it applies to only one part of the equation, we can use the log trick now. Log trick is that uh, if you have if you have this form of equation, then we know that the derivative of the log fx is actually 1 upon fx, and then you take the derivative of whatever is inside. So nabla x, or gradient of log fx, is basically 1 upon fx times the gradient of fx. And therefore, the gradient of fx, the gradient of p theta, is actually equal to p theta times gradient of log p theta. So that's what we're doing here. The gradient of p theta is p theta times gradient of log p theta, and the other term stays there. So here we're using the log trick. Then after we have used the log trick, we can compute. We can say that this is the same expectation. We can close the expectation because this can be a probability distribution. And this is the rest of the term. So if we close the expectation, then the expectation is like hides the probability term, but the other terms that show up are the log p theta gradient of that, and the reward at time, and the reward of the trajectory. And then we can say that the log p theta, the gradient of log p theta, is actually equal to the summation of log pi theta gradient for multiple steps. And how this happens can see in the next slide. So roughly, what is log pi theta and what is the gradient of log pi theta? Well, the probability of tau, or the trajectory, is actually probability of the first state, then the probability of taking an action at and uh, st according to a policy pi theta, and then transitioning to st plus 1 given st and at. So this is the equation that you get from factorizing the Bayesian network, or or this thing, or this graphical model, because it's saying that the probability of the trajectory is probability of s1 times the probability of a1 given s1 times probability of s2 given s1 a2 a1, and then probability of a2 given s2, and so on until the end of the trajectory. So this part is actually the factorization part of the graphical model that we have uh, for the agent, or for the MDP. And then we can take a log on both sides. If you apply log on both sides, you get log p tau is equal to log p s1 plus summation of log p of this, summation of log p of this. And you notice that theta actually only comes on in the third part. It doesn't actually come here or here. So when you take the gradient with respect to theta, you'll only get the gradient of this part, which is the gradient of log pi theta atst. And that's how we replace this part with gradient of theta log pi theta atst. Okay. So, and because of this, the final equation is that we'll have the reward. So basically, we can sample many trajectories and collect the rewards. And as we are collecting the rewards, we can compute this from a policy network, and then use this policy gradient to update the policy parameters. I'll explain how to do that through a concrete algorithm. But before that, before we go further, any question in this equation or this derivation? I'll just wait for a minute. But is there any question in these three parts? Okay. I just move on then. Like, you can ask me questions later on as well. But I think the way I expressed it, it shouldn't be too difficult to follow why we get this term. So what we are doing here is that we are trying to do gradient descent on the parameters of the policy. And to get an update rule for that, we use gradient descent. And in the gradient descent part, we need to compute the gradient of some score function or some function which tells us how good the parameters we have are, and do that, we say that j theta is expectation of r tau, which is a reward of the entire trajectory, and then using the expectation, computing this expectation, the gradient of this expectation comes out to be this term, which can be computed by hand, um, which can be computed like manually once we have a couple of trajectories, because we can compute this gradient as well using autograd or any other technique. So like that's the equation that we have for uh, policy gradient. Okay. So note that while I've discussed and shown you that there is this form of policy gradient, there are other forms of policy gradient as well. And in practice, basically, there is a form of form of policy gradient where this bracket is not outside but it's inside, and everything is multiplied by some psi, some function. So there are many variants of policy gradient. One variant is where the psi is equal to r tau, or the reward of the entire trajectory. As we just saw, this is equal to this part, because even in this, there is a component r tau which can be moved inside, and that is a psi t. Psi t could also be the return starting from step t, or it could also be the return minus the baseline value, which a baseline is subtracted to reduce the estimate variance. So this is an estimator of the gradient update we need to do, and this is usually very high variance. So to reduce the variance, we can do a gradient a gt minus bt, and other forms are there as well, but we'll discuss it as we see necessary. But in general, the main takeaway from this is that you can have a policy network, and to update that policy network, you can use the policy gradient technique. And the policy gradient technique is basically this equation, which can be computed once you have some trajectories. And there are many variants of it, and the variants are similarly like you can derive them the most you can derive them similarly to the way I derived this equation, but some of these equations are hard to prove, but they all exist. So don't worry about like how what side we should choose. Side depends on how you want to improve your policy, and it like which one is the best side. Well, there's a paper called Generalized Advantage Estimation, or GAE, which discusses these kinds of problems. Like what is the best estimator we can use. See, so they're discussing that this is the policy gradient theorem. I don't know if you can see this, but they're saying the gradient is equal to this term. Like I said, it is equal to this term times the psi t, and the psi can be one of these following terms. So if you want to read to this paper, the paper's name is GAE. So the name is High Dimensional Continuous Control Using Generalized Advantage Estimation, and GAE is just this part. Yes. So I hope like I made it clear that there are many variants of this, and we'll be discussing like one variant of this. But there are other variants which you can use to update your parameters for the policy, and that's what the notion of policy gradient is. It's trying to update the policy. It's trying to update the policy by a gradient approach, and in the gradient approach, you need to take the derivative of some score function, and the score function is telling us how good the um, desired policy or the current policy is. Okay. All right. Any questions so far? Okay. Um, okay. So let's think about what is the actor-critic method. So like I said, like you've seen this term like being thrown away, thrown out like so many times. But what does it actually mean? So in actor-critic, basically there's two networks. One is an actor, which takes in a state and gives you the action to act, and there's a critic which tells you how good the actor is at any point in time. So we can use this. We have the two networks: policy network and Q network, and they're updated using different techniques. The policy network is updated using the policy gradient technique, and the Q network is updated using the Bellman update. And this is the formula for the policy network that people use in active critic. They use psi equals the Q value. Like I said, like we proved it for the reward, but it can be many things. It could be gt minus bt. It could be reward r tau, but it would also be the q value. So we use this method to update the actor, and for the critic, we update it using the Batman update. So any question on this slide? Because if you understand this part, it's very easy to grasp what is happening in the uh, future uh, DDPG algorithm. Okay, so if nobody has any question, then I can just show you an example of an actor-critic method. So in an actor-critic method, I just said that this part, the policy is changed using the policy gradient technique, and this part of the policy is changed using the Bellman update. So the actor update is basically the same. It's Since we know that this is the way you update the policy gradient, so we take this part, we put in the q value, and q value times the gradient of this is what we had here, and we do it for every time step, and that's how you update the actor. And then we have uh, for the Bellman update, we have the reward plus gamma times some q value at the next step minus q, uh, and then this part is multiplied by the gradient, which is this is a semi-gradient update. But usually we can just do a square. You can take a square of this, and that gives you the error, and you can use machine learning techniques like AutoGrad to compute this gradient by yourself, and then use this gradient to update the weights of the critic. So the algorithm goes like this actually. uh, the first sample the reward and next state, sample the next action according to the actor. We update the actor parameters by using the policy gradient technique. And in the policy gradient technique, you can see already there is a log term here and then there is a side term here. And we are doing this for every time step. So we do it for every time step. So we are for every time step we are sampling the reward, next state, the next action, and then we are updating the parameters of the policy, and then we can compute the parameters of the, like we can change the parameters of the critic, uh, and that's how we get the actor critic algorithm. This is the actor critic algorithm, which is on policy. By on policy, I mean that there's no replay buffer. There is and there is the network you're changing is the network you're using to explore the environment. In short, your behavior policy is the same as your optimized policy. We discussed like on policy last time as well, if you remember a little bit. Okay. Now, if you know the on policy actor critic, then uh, let's move on to deterministic policy gradient or DPG. So in deterministic policy gradients, we obtain a policy gradient by formulating another type of long-term reward objective. So why did we discuss all this? Because for like essentially it is necessary to know what the policy gradient technique is before you start knowing what this kind of policy gradient does. So the previous policy gradient was like based on this objective here. This objective here is what it was based on, long-term expected reward. But and the current one will be based on a different thing. It will be based on this term here. So I know it's hard to understand what's happening here, but let's unpack here. Like let's try to see what's actually happening here. So we can compute what is happening is that we are maximizing our theta, and the theta star or the best theta is the maximization of this value, and this value is basically you choose a state according to your visitation distribution, and then for that state, whatever is the q value using the deterministic policy uh, is the this q value, expected q value is your j theta. So the best we measure how good a policy is using j theta, which is the expected q value we get by following policy pi theta. So it's saying that how good a policy is dependent. It can be measured, quantified using how good the q value is when you start from S and take the actions only according to policy pi theta, where theta is um, what we are optimizing about, what we are optimizing for. So that's how we get this part. And when you open the expectation, this is how you get
You're mute.
sorry, yeah, can you guys hear me now?
Yeah.
Yeah, sorry, I lost the internet for a while. uh, Let me just go back to the slide. Okay, so I was discussing, I think I was discussing this part, deterministic policy gradient. Wait a second, am I recording? Yeah, it's recording. Okay, so the reason that we have this kind of an objective rather than the other kind of objective is that we want, we have this other notion of maximizing the long-term discounted reward, which is that you can say that a actor is good if if the expected q value when you start from a state S and you choose the action according to that policy parameters, you start getting good you start getting good values. So you start getting good expected q values. So that's how you measure how good a policy is. And when you open it up, the expectation gives you the discounted distribution, state visitation distribution, and the q value. Now, it might be it's a good question, like what the state vegetation distribution is and why does it look like this? Well, it does look like frankly, like this is outside the scope of like in 1 hour presentation of why you should, why did we choose this kind of a policy gradient formulation. But know that it's another formulation that we have. And if you want to look at the proof for this, you can just look at the proof in the paper for DDPG. Like they don't have it, but the DPG paper has it. So the DPG paper is called Deterministic Policy Gradient. And Deterministic Policy Gradient paper by David Silver is has these equations with proofs. I think they show proofs. We have the appendix as well. So, well, if you just go there and figure out what the, if you go there and you need the proofs, it's in the appendix of the full paper. So, for anybody who's interested in knowing how the state vegetation distribution works, you can just go there and know about it. But it's outside the scope of this discussion that we're having right now. So, in general, what I'm talking about is that once you have this policy objective, then you can compute the nabla theta or the gradient of this objective by moving the gradient term inside the integral sign. And when you move it inside, this part doesn't depend on theta, and only this part does. And when it does, you can take the gradient with respect to take the gradient of this with respect to theta. You can instead take the gradient with respect to action A, and then you can take the action and take the gradient of that with respect to theta. So this is a chain rule, and this is basically the main equation that DDPG has. To compute the policy gradient, you just need to compute the gradient of expectation of this value and times this value. Like this part seems, I hope this part seems intuitive enough, because what we are doing right here is simple. We are taking this q value and we want to take the gradient of this value with respect to theta, and we don't have theta right away because this q network is a network in itself. So what we will do is we'll use chain rule, and we'll say that the gradient of this with respect to theta is gradient of this thing with respect to the action and times the gradient of the action with respect to theta. And the action is always pi theta because this is a deterministic uh, uh, policy. So that's what is happening in this slide. So here's an example of DPG with online actor critic. Similar to before, the only difference is that previous time we were using the policy gradient method, policy gradient technique here, but now we're using DPG technique. So if you see the equation, the equation that we were looking at, this was the equation we were looking at for on policy actor critic. And in this, we were using the policy gradient technique, which we discussed here. But in the deterministic policy gradient technique, we have the deterministic policy gradient that we're using, um, as we discussed, like as we showed right here. So this is the part we're using because this is an expectation. This part is what contributes to the actor update, and the critic update is the same as before. So any question on why we like how did we get this update? It's very similar. It's simple to you understand it because frankly you just get it using chain rule on the policy gradient on the j theta that we define for deterministic policy gradient. Um, yeah. So any question on this slide? Because if you know this part, then you basically know most ingredients about DDPG. Okay. Um, okay. Let's go to actor DDPG. And then this is the final most important slide, I guess. But what are the features of the DDPG? First of all, it's the first going to the features, we need to know that it's an actor critic approach where we combine DPG for learning the actor with DQN, which is correspond to the critic. And the features are that the actor learns using the DPG update, and the critic learns using the Bellman update. A replay buffer is maintained where when you go through the when you go through the experience of when you go through the process of collecting experience, you put it in a replay buffer and you sample it over time to learn from that. And a copy of both actor and critic is maintained, updated slowly over time. So basically, the value of the there's two networks that we have for actor, both actor and critic. They have total four networks, and each of the network, like there's one copy of actor network and one copy of critic network, and each of those are updated very slowly over time. So there's two networks which are there to make the learning more stable. It stabilizes learning. Um, So another thing is that batch normalization may be used, and we will see that actually batch normalization makes sense. It makes sense to use batch normalization. And another thing is that noise is added to help explore, because if you just look at the output of the pie, you will not like it won't explore as good. So we add noise according to some process to help the actor explore. So any question in DDPG, because I'll just go to the result next. Okay, so if you don't have any questions about this, then basically you know most of the pieces of DDPG, and I'll just quickly go to the algorithm because it's really simple to do that. Now that you know most of the pieces, you can see that we initialize the actor critic network, we initialize a copy of those networks, then we initialize the replay buffer, then we go to the multiple episodes, we initialize a random process, which may be Ornstein or Ornstein Uhlenbeck. We receive an initial observation state as one. Then we select an action according to mu, or the mu here is the pi plus noise. Then we execute it and observe reward new state stored transition, sample on mini batch of transitions, then update the target values for Bellman update. Update the critic first by doing the MSC error, then update the actor policy using these policy gradient, deterministic policy gradient technique, and then we move then we slowly update the target networks u dash and u dash by taking the previous old values and adding a very small tau to the current value of theta q. So this is like tau is very small. That's why the values of this will change very slowly, because this part is very close to one. So this part will be the more dominant factor in updating this part. Okay. Any question in this algorithm? So if you don't know, if you don't know understand anything, then you can just stop. You can stop me here and ask me questions. Okay. Um, so in terms of results, there's a video we can watch. But in general, they have these tasks of card pull swing up, reaching, grasp and move, puck hitting, one upper balancing, and there are two tasks for locomotion. And there's also a racing environment. Those videos they have, and we can go through those videos. But before we go through them, this is their graphs for training, and what we can gather out of this is that you can see the green lines are always at the very top of this, and the green lines are the ones which correspond to target networks and batch normalization. So in general, if you create target networks and create copy of the networks, it stabilizes the learning, and with batch normalization it becomes even better, and so it performs the best overall. And we will see the video and then we'll conclude. Okay. This is the cardboard swing up task. 3 degrees of freedom reaching task. You have to reach a certain ball which is on the left side of the screen. Gripper is where you have to grip an object and go to the other side and put it to the other side. These are all very robotics environments. Like, yeah, I think this notice makes sense. There's this balancing task which has to balance. This is the block wall task. You have to put the block there. It's a locomotion task. This is a gripper task. This is another locomotion task. This is puck striking, where you move the puck and it should go to the hole. Then this is pendulum swing up and this joint reaching, cardboard swing up, reaching, monopod. You can see like there are many updates, and this is for talks. This is a car racing environment in which you have to move forward. As seen by the agent, like has a very the agent only sees a blurred version of this because there's dimensionality reduction in the convolution network. All right, to conclude, uh, what we discussed today was DDPG. DDPG is an off policy. It's yeah, I mentioned it late, but basically it's an off policy algorithm just because it has a replay buffer, and the learning that you're doing is by sampling the mini batch from the buffer, uh, and the behavior you're doing is using the exploration policy noise. So that's why like it's off policy because the two policies are different. The one used for learning and the one used for doing behavior. So we discussed today DDPG, which is an off policy arithmetic method, which uses a deterministic policy gradient update. We combine DQN and DPG. That's how we get DDPG. It works with contained action spaces. It is scalable to large action spaces, and it requires fewer steps of training to achieve success than by DQN. Okay, that's pretty much it for today. If you have any question, you can I'll pause for a second. You can ask me. So yeah, any questions here? Okay, I guess then that's pretty much it. Thanks for attending.